Our next speaker is Deby Fapyane, and she is a PhD student at iNano. So she's going to, in one moment, give us a little talk about her particular research. And I'm excited because she's a PhD student. So this is really cool work from a PhD. I mean, this is really wonderful. So we're really excited. I think so. I think it will be.
I will share how will it be and how will it feel to be nano-detective in the unseen world. Basically, you cannot see your tool, you cannot see the samples, so you blind both ways. Yes, the title is How to Use the Nanotechnology for Detection of Bacteria in the Water. And this is actually correlated with my PhD project. It's about making cheap, disposable biosensors for bacteria detection in the environment. So it's not only the water, but it's only in the air. Particulate, we have a collaborator in Roskilde, and we are using particular methods to measure it called electrochemistry. It's not as scary as it seems. And I would like you to see like this bolt here, cheap and disposable biosensors. So how many of you like traveling here? Yes, me too. Probably when you're traveling in Europe area, as you see here, which is low risk, and so it means that high hygiene level, you will not think so much drinking the water in that particular area. It's Europe, everything's clean. But when we want to have some kind of exotic holiday to this area, then you need to start thinking, how is the water there, and so on. Probably not that bad, but you have this kind of thinking. And actually, they make this high risk potential for the low hygiene level because one theory states that it's because it's dense population. When you have more dense people, then you have worse relations with the environment. Worse, like dense people, you have only one water body. You do everything in that water. You drink, you also take a shower, you do everything. So it means that there is high risk of the other contamination. And while this contamination happening in our environment, actually, based on the history, the environment monitoring of the bacteria in the environment already started in the 1800s. When Dr. Josh Snow, he studied about the cholera outbreak in London. And probably this is our face. If we see like, oh my God, this is the water and with full of monstrous fall that we don't know. And actually, because they are unseen, as I told you, how do we know that they are there? There is several methods to know, which is kind of a standard method. First is, of course, a microscopy first found by Anton van Leeuwenhoek, the one that actually discovered or observed the first bacteria in 1500. This is the old one, very cool stuff. And then it evolved until the scanning electron microscopy. It's actually the microscope that Marianne used to see her particles. When you want to monitor the bacteria in the environment, it's not possible to have this SEM, right? Like you are taking and then, okay, see sample here. So it's not practical. There is another method called bacteria culture and plating. Basically, you take the sample or take the water, you smear it in the culture and wait for 1 day until they grow, if they grow. If not, because actually only 1% of bacteria population can be grown. So the other, you never know. So that's why you then have the third one with a molecular tool using the DNA of the bacteria. So you take the sample, you purify the bacteria, and then you amplify them. So it's like a more number, it's easier to see, right? So when you with this PCR tool, it's called polymerase chain reaction. So when you have amplified DNA, then you just like put it in this gel electrophoresis and okay, this is my bacteria, whether it is a specific bacteria in your sample. But if you want to purify the DNA, sometimes it's complex and also prone to contamination from you, because you are working, probably something coming down to your sample, then actually you're detecting yourself. So it's not a funny thing to do. Yes, and then the fourth tool from the biochemistry is bioassay called enzyme-linked immunosorbent assay. It is used a molecule called antibody that actually can recognize specifically what kind of bacteria that you have in the sample. So you have like 4 techniques, different direct, indirect. So all of this technique, yes, they are some of them they are sensitive, some of them they are also time consuming, is highly costly. And then World Health Organization state, okay, because we are using water so much, then it must be examined regularly and frequently, because like the changing of the pollution and so on. And then they say it's better to examine the drinking water frequently by simple tests than several tests in the complicated way. So basically, if you can just go to the environment, you take the sample, you have a machine that you can just put your sample and say, this is polluted. That must be easier, right? And that one is what we called biosensors. Biosensors is devices that comprises on the 2 parts, which is one, bioreceptors that they can recognize specifically what is your sample. So if you want to detect virus, bacteria, or any others. And then you have a transducer. It means they recognize the changes of the molecule interaction here, and they transduce what is the signals. And then the signals goes to the computer and data processing and so on. And as I told you before, that we are using the electrochemical biosensors, it's sensing the changes of the electron behavior on the electrode. There is oxidize and reduce, and they just measure this one. And this is how it look like in the lab. And this one, the one that we want in the environment. And we have a collaborator working on this. So you can just go to the environment, have your sample detected, you know what is the status of your environment. And then you have a lot of bacteria, as you saw in the paintings before. So there's a lot of how to catch specifically like one bacteria that you're interested in. For example, E. coli. Then you need to have specific methods how to do it. And first, the specific method is to use the direct detection of a bacterial cell. And there are 3 techniques how to do it. You can use the label-free, just by the attachment of the bacteria, and then with label and sandwich assay. And this method, there is some increase of sensitivity. And why actually we are care about the sensitivity? Because the World Organization say, I want that there is no bacteria in 100 million sample, and there is only one bacteria in 1 liter. And when you have like this sample, and you have to find something in micron size, then it means that your sensors should be sensitive enough to do this. And okay, sensitive, it means that you have to catch it carefully. But with what? If you want to catch bacteria, there are several biorecognition molecules that they can just catch the bacteria specifically. You can use DNA aptamer. You can use the virus that actually they infect the bacteria. So an antibody that I told you before, and this is a carbohydrate. This is the cheapest option to catch the bacteria. And labels is actually the one that gives signals in the biosensors. Labels can be from nanoparticles. This is usually the one that they use is the nanoparticles, the one that you have in your LED TV. So you can get like a red color, fluorescence green, fluorescence blue, whatever you want. And another one is you're using enzyme. And this is the particular case in our study that we are using these all biosensors on the magnetic beads. Why we are using the magnetic beads? Because it's very easy to collect your bacteria just by putting the magnet. So you have the sample this size. You put the magnetic bead in. You just mix it like this. You retrieve the magnetic beads, just your magnet. You just buy like the magnet where you're traveling in from Hamburg, the magnet, and you put it in your sample and you retrieve the magnetic beads. It's very easy. Everybody can do it. And when there is no bacteria, no signal. If there is bacteria, then there is a signal. And the increase of this signal is depending on the amount of bacteria that you have in your sensors. And this is some of the results that we have. That actually we already achieved the limit of detection of 1 cell per 10 milliliter. We need to increase, of course, until 100 milliliter per 1 liter, but currently this is the most sensitive technique. And actually the sensitivity of the system, it depends on what biorecognition molecule that you are using. Antibody, okay, they're big, they're small signals. Aptamer is more flexible, so they have a very high signal. And of course, your biosensor should be specific only for one particular bacteria that you want to detect. It doesn't detect other bacteria. For example, you want to detect E. coli. So when you have bacillus, for example, here, they don't say, okay, there's nothing here, because you just want to detect only one particular bacteria. And the other way is you can use detection of the DNA of a ribosomal RNA in the sample, but it is more complicated. You have to break the bacteria and then they will release the ribosomal RNA, then you detect it with the same principle. And this is also our result. We are using synthetic aptamer, and then to detect the bacteria, how it changes the signal depends on the amount, but still the result is much less than the direct detection of bacteria. And the last one is the detection by the bacterial metabolism. So when they are caught by your biosensor, you are waiting until they are breathing and eating something. Of course, then it takes time. If you have more bacteria, it's easier to detect, but if you have a small bacteria, then you are waiting until you have the accumulation of the product and so on. So we haven't done this one, we're still planning. So what is the take-home message for this presentation? I will advertise the biosensors, of course, is my research, that it offers you a simple, cheap detection bacteria in the water. And this particular method, electrochemistry, they provide sensitive and also miniaturized on-site monitoring that you can just go to your site and then take the sample and you get the answer directly. Oh my God, there is a fecal contamination here. Just block everything and then we treat this area. And probably can be a traveler first kit. When you go to the exotic place, you have these kits and you will no longer be scared of your water. And thank you for the people that already support this research, and thank you for all for listening.
That is really cool.